Hi everybody, this video is going to talk about how to solve systems of equations, two variable systems of equations using the inverse matrix method and also row operations. All right, so these are the two examples we saw in class today. I'm going to go ahead and make this video so you guys can pause, rewatch, rewind, whatever you need to understand it. Okay, so with the inverse method, the goal here is to turn this into a matrix equation. Okay, our first matrix is going to be just the coefficients from our system. And we're going to multiply that by the variable matrix, just xy, the variables we have in our system. And that's equal to the constants. All right, and I want you to label them like this. Okay, let's call this matrix A. Let's call this matrix X and this matrix B. Okay, so we essentially have matrix A times X equal to matrix B. Now, the idea behind this is in order to solve for matrix X, which has our variables, what we need to do is get rid of or cancel out matrix A from this side. So the idea is if I multiply each side by the inverse of A, it's going to cancel out with the A here, and then we have to keep it balanced, so we're going to multiply this side by the inverse matrix. Now, what we end up getting here then is matrix X is going to be equal to our inverse matrix times our constant matrix. Now, you have to make sure that it goes in this order. You cannot reverse B times the inverse of A because we won't be able to do the dot product. The dimensions won't line up. A inverse is going to be a 2 by 2. B is a 2 by 1. So this is the only order we can actually multiply those two matrices in. So here's what we need to do next. We need to actually find what the inverse of A is. And we need to do that by first finding the determinant. So to find the determinant of A, we're going to go back to matrix A, and we're going to do negative 4 times 14 minus negative 7 times 6. Okay? And when we do this calculation, we get negative 14 for the determinant. So we're going to use this value to actually find our inverse matrix now. We can find the inverse of A by doing 1 over the determinant times, and then we're going to do a variation of matrix A here. We're going to take the negative 4 and 14, and these two actually swap spots. The negative 7 and 6 stay where they are, but they change signs. So now when we do this scalar multiplication, we end up with negative 1, negative 1/2, 3/7, and 2/7. So we have found matrix A inverse, okay, the inverse of A, and now what we need to do is take that and multiply it with matrix B to actually solve. All right, so last step here. We're going to find matrix X, which is our variable matrix, by taking the inverse matrix we just found, and multiplying it by our constant matrix, which was B up here, negative 15 and 12. So we're going to actually multiply these two matrices together now. So we're going to do top row times the column here, the only column in matrix B. So we're going to do negative 1 times negative 15 plus negative 1/2 times 12. Okay, that calculation will give us the x value of the solution. And then we can take our bottom row times the column, so 3/7 times negative 15 plus 2/7 times 12. And then we're going to go ahead and we're going to actually calculate what these rows give us. So our top row, when we type that into our calculator, is going to give us 9. Row is negative 3. So our solution to this system that we started with is 9, negative 3, and we can write that as an ordered pair. So that is the inverse method. Now, row operations. We need to start by making what's called an augmented matrix. So essentially what we're doing is we're taking our system and we're basically removing the variables, and instead of the equal signs, we're going to have a bar. So we're going to take our first equation, 9x plus y, okay, 1y, and equal to 12. And we're going to organize it into this augmented matrix. We're going to do the same thing to our second row. And now we can start doing some row operations. Now, a couple of things to remember here. I was able to turn this into this augmented matrix because my x values, y values, equal signs, and constants were already lined up, similar to how we stack equations in the elimination method for solving systems of equations. So here's what we want to do. Off to the side here, we want to make sure we're recording the row operations that we're performing. And on the right, we'll actually write down our new matrix for each step. So here's what I notice. We know that we need to get a 0 in one of these two spots. Okay, because to solve, we're trying to get our augmented matrix in this format. So to get a 0 in one of these spots, and it doesn't matter which one, just find the easiest path. What we could do is we could take the negative 18 and we could do 2 times 9. Okay, and the reason I would want to do that is if I do negative 18 plus 2 times 9, I'm going to get negative 18 plus 18, which results in a 0. So I'm going to write that as a row operation. We're going to say row 2 is going to become what was in row 2 plus 2 times what's in row 1. Now, we're only changing row 2. Yes, we're doing a plus 2 times row 1 in our calculation, but we're not going to actually change row 1. We're just going to use that as an in-between step. So our new matrix will have the exact same top row. So let's go ahead and just copy that down. We have 9, 1, 12 in row 1. Now row 2, I'm going to do negative 18 plus 2 times 9, so we get 0. We're going to do 7 plus 2 times 1, get 9. We're going to do 3 plus 2 times 12 to get 27. So the only thing that changed was row 2. Now, once I have a 0 in that location, we want to go ahead and get a 1 here. Okay, instead of that 9, we want a 1. Now, here's a nice little tip. Once you get to this point, you can always just multiply this row by the reciprocal of the value that's in that one spot, and it'll turn it into a 1. So what I mean by that is I need to multiply 9 by its reciprocal, 1 over 9, to turn it into a 1. And if I'm going to multiply that one by a 9th, I have to multiply the entire row by 1/9. So here's our next row operation. Again, the only thing that's changing is row 2. So I'm going to go ahead and just copy down row 1. Now for row 2, we have 0 times 1/9, so that stays 0. 9 times 1/9 is 1, and 27 times 1/9 is 3. So now we can see that our bottom row in our matrix right now matches the bottom row in what we're trying to get here. So now we need to start working on our top row. Our top row needs a 0 right here, and we want to get that 0 before we work on getting the 1. So the nice thing is, I have a 1 in my top row and a 1 in my bottom row. I can just take my top row minus my bottom row to get that 0 that I'm looking for. So our next row operation is going to be, we're going to get a new row 1 by taking what was in row 1 and subtracting what's in row 2. Now, again, the only thing that's changing here is row 1. We're using row 2 in our calculation, but row 2 itself is going to stay the same. So I'm going to go ahead and just copy down row 2. So here's what we're going to do. We're going to do 9 minus 0, so this stays 9. 1 minus 1 we said gives us 0. And then 12 minus 3 gives us a 9 here. So our last step is we need to make this 9 a 1. So we're going to multiply that row by 1 over 9. So this is our final step. 9 times 1/9 is 1. 0 times 1/9 is 0. 9 times 1/9 is 1. And then my bottom row stays the same. So what this is really telling us, if we kind of take this final augmented matrix and think about how we converted from our system to the original augmented matrix, what this is really telling us is we have two equations. We have the equation 1x plus 0y equals 1. We also have a second equation, 0x plus 1y equals 3. So if you remove the 0 variable portion of each equation, what we're really left with is x is equal to 1 and y is equal to 3. So what we found at this point is the solution to our system, and if we write that as an ordered pair, we would get 1, 3. All right. Please make sure you rewatch, rewind, pause, and come in and ask questions tomorrow if you're still not sure how to do either of these methods. Have a great day.